Hello everyone, welcome back to my channel InfoSec Lab. Today we are going to talk about OAuth 2.0, the backbone of app authentication and authorization. Think about how apps like Instagram, Spotify or Uber that ask for your permission to access your Google account, photos of payment information. That's the OAuth 2.0 in action. In today's TryHackMe's room, we're going to go over the essential concepts of OAuth 2.0, how to identify OAuth services, how to exploit these services, and last but not least, how to protect ourselves from attackers exploiting these services. The key concepts when it comes to OAuth 2.0, there are several key concepts that we have to get familiar with. First of all, resource owner. The resource owner is a person or a system that controls certain data and can authorize application to access the data on their behalf. This concept is fundamental as it centers around the user consent and control. For example, you are the resource owner as a coffee shop customer. You can control your account information and grant the coffee shop's mobile app permission to access your data. Client. Client can be the mobile app or a server-side application. It acts as an intermediary, requesting access to resources and performing actions as permitted by the resource owner. For example, the coffee shop's web app, which you use to order and pay for coffee, is the client. Your authorization is needed to access your account details and payment information. Authorization server. The authorization server is responsible for issuing access token to the client after successfully authenticating the resource owner and obtaining the authorization. The authorization server plays a crucial role in the OAuth process by ensuring the client is granted permission only after legitimate user authentication and consent. For example, the coffee shop's backend system that handles authentication and authorization is the authorization server. It verifies your credentials, grants the web app permission to access your account. The resource server. The server hosting the protected resources can accept and respond to protected resources requests using access tokens. The server ensures that only authenticated and authorized clients can access and manipulate the resource owner's data. For example, the resource server is the coffee shop's database that stores your account information, order history, and payment details. It responds to requests from the web app, allowing it to retrieve and modify your data. Authorization grant. The client uses a credential representing the resource owner's authorization to access their protected resources to obtain an access token. The primary grant types are authorization code, implicit, resource owner password credentials, and client credentials. For example, when you first log in the coffee shop's app, you are given an authorization grant, like entering your username and password. The app uses this grant to get an access token from the authorization server. We'll discuss this in details in the next task. Access token. A credential that the client can use to access protected resources on behalf of the resource owner. It has a limited lifespan and scope. Access tokens are essential for maintaining secure and protected communication between the client and resource server without repeatedly asking the resource owner for credentials. For example, once you log into the coffee shop's app, it receives an access token, which allows the app to access your account to place orders and make payments without asking you to log in again for a specific period. Refresh token. A credential that the client can use to obtain a new access token without requiring the resource owner to re-authenticate. Refresh tokens are typically long-lived and provide a way to maintain user sessions without frequent login interruptions. For example, when your access token expires, the web app will use a refresh token to get a new access token, so you don't have to log in again. Redirect URI. The URI to which the authorization server will redirect the resource owner's user agent after the grant or denial of authorization. It checks if the client for which the authorization responses have been requested is correct. After interacting with the coffee shop app and logging you in, you will be redirected to the authorization server by the app page in the coffee shop's app, commonly known as the redirect URI, to confirm that you have successfully logged in. Scope. Scope are the mechanism for limiting an application's access to a user's account. They allow the client to specify the level of access needed and the authorization server to inform the user what access levels of the application is requesting. Scopes help enforce the principles of privilege. For example, the coffee shop's app may request different scopes, such as access to your order history and payment details. As the resource owner, you can see what information the app requests access to and grant or deny permissions. State parameter. An optional state parameter maintains the state between the client and the authorization server. It can help prevent CSRF attacks by ensuring the response matches the client's request. The state parameter is a crucial part in securing the OAuth flow. For example, when you initiate the login process, the coffee shop's app sends a state parameter to authorization server. This parameter helps ensure that the response you receive is linked to your original request, protecting against certain types of attack. Token and authorization endpoints. The authorization server endpoint is where the client exchanges the authorization grant or the refresh token for an access token. In contrast, the authorization endpoint is where the resource owner is authenticated and authorizes the client to access the protected resources. By familiarizing yourself with these topics, you will easily understand the exploitation techniques and associated vulnerabilities in the upcoming task. Okay, so which optional? Let's try to take a look at TryHackMe as an example. I'm trying my best to explain. Oh no, this is the wrong VM. I'm going to try my best to use TryHackMe as an example to explain these concepts so you can easily understand them. No, admin. Okay, so I am, as the user, is going to be the resource owner. I have my own username and password, so I'm going to be the resource owner. The client, in this case, is going to be TryHackMe website. So over here, when I click continue with Google, TryHackMe is going to be a client, and the authorization server is going to be the Google Gmail. So when I click continue with Google, I'll be redirected to the Google login page where I'll input my Gmail account and the password for that Gmail account. And Google authorization server will authenticate me, meaning that I will be signing in using my Gmail account. The resource server is going to be the Google's database that stores my personal information, like my first name, last name, email address, phone number, etc. Those are the terms for OAuth. Authorization grants. So these are different grants. When it comes to OAuth 2.0, there are different types of tokens and authorization codes exchanged between the authorization server and the client, and which we'll discuss later in this room. But for now, we can skip authorization grant. The access token, the same thing, we'll explain later. Refresh token, we'll explain later. Redirect URI. So after we have successfully logged in our Gmail account, we'll be asked to grant TryHackMe permission to access certain information. And once we grant the permission or deny the permission, we'll be redirected back to the TryHackMe login page or maybe dashboard. And that's going to be the redirect URI. The scope is going to be determining what kind of information that TryHackMe has access to. So let's say in this case, TryHackMe only needs to access my personal information like my first name, last name, my Google Gmail account, and that's it. It doesn't need access to my payment information. It doesn't need to access my photos. So those are out of scope. And state parameters, token authorization endpoint, these are going to be talked later in this room. All right, let's continue. Answer the questions. Which optional parameter can be used to prevent CSRF attack? That's state. What credentials can client use to access protected resources on behalf of the resource owner? That's access token. Okay, OAuth grant types. OAuth 2.0 provides several grant types to accommodate various scenarios and grant types. These grant types define how an application can obtain an access token to access protected resources on behalf of the resource owner. In this task, we'll discuss 4 primary OAuth 2.0 grant types. The first one is Authorization Code Grant. The Authorization Code Grant is the most commonly used in OAuth 2.0 flow, suited for server-side applications like PHP, Java, .NET, etc. In this flow, the client redirects the user to the authorization server, where user authenticates and grants authorizations. The authorization server then redirects the user to the client with the authorization code. The client exchanges the authorization code for an access token by requesting the authorization server's token endpoint. This grant type is known for its enhanced security, as the authorization code is exchanged for an access token server to server, meaning the access token is not exposed to the user agent, thus reducing the risk of token leakage. It also supports using refresh token to maintain long-term access with the repeated user authentication. So going back to our TryHackMe example, I am the resource owner right here as a user. I land on TryHackMe page, which is the application right here. I want to log in using my Google Gmail account. Once I click this button, I'll be directed to the login page to log in my account. Right here. So over here, I'll be entering my Gmail account with a Gmail password. Once I successfully logged in, I will be asked to grant TryHackMe permission to access my personal information. And once I grant the permission, as explained earlier, I'll be redirected back to TryHackMe dashboard, meaning that I have successfully logged in using my Gmail account. In the backend, when I'm redirected back to TryHackMe dashboard, an authorization code is sent back to the TryHack server. TryHackMe server will use this authorization code to request an access token, which later will be used to request resources on Google database. Implicit Grant. The Implicit Grant is primarily designed for mobile and web applications where clients cannot securely store secrets. It directly issues the access token to the client without requiring an authorization code exchange. In this flow, the client redirects the user to the authorization server. After the user authenticates and grants authorization, the authorization server returns an access token in the URL fragment. This grant type is simplified and suitable for clients who cannot securely store client secrets. It is faster as it involves fewer steps than the authorization code grant. However, it is less secure as the access token is exposed to the user agent and can be logged in using the browser histories. It also does not support refresh tokens. So the workflow is the same. I land on TryHackMe, click continue with Google. I'll be taken to Google login page. After I successfully log in using my Gmail account, I'll be asked to grant TryHackMe's permission to access my personal information. Once I grant the permission, I'll be redirected back to TryHackMe page, but this time Google Authorization Server send the access token directly to TryHackMe via the URL fragment. And because it's in the URL fragment, it is vulnerable to man-in-the-middle attack. It can be intercepted, and there are risks of token leakage. Resource Owner Password Credentials Grant. The Resource Owner Password Credentials Grant is used when the client is highly trusted by the resource owner, such as first-party applications. The client collects the user's credential, username, and password, directly exchange them for an access token as shown below. So I am, as a user, will provide my username and password, my Gmail account, and password for that Gmail account to TryHackMe. In the backend, TryHackMe will use this setup credential to authenticate against the authorizations Google Gmail server. And once they successfully authenticate against Google Authorization Server, they'll get an access token, which they will be using to request my personal information on Google database. It is less secure because it involves sharing credentials directly with the client and is unsuitable for third-party applications. Client Credentials Grant. The Client Credential Grant is used to is used for server-to-server interactions without user involvement. The client uses his credentials to authenticate with the authorization server and obtain an access token. In this flow, the client authenticates with the authorization server using its client credentials. The client is secret, and the authorization server issues an access token directly to the client, as shown below. Okay, this grant type is suitable for backend services and server-to-server communication, as it does not involve user credentials, thus reducing the security risk related to user data exposure. In the next task, we show how the OAuth flow works within an application. What is the grant type often used for server-server interaction? Client credential grant. Okay. How OAuth workflows. The OAuth 2.0 flow begins when a user or the resource owner interacts with a client application and requests access to a specific resource. The client redirects the user to an authorization server, where the user is prompted to log in and grant access. If the user consents, the authorization server issues an authorization code, which the client can exchange for an access token. This access token allows the client to access resources server and retrieve the requested resource on behalf of the user. Alright, so we've explained this. Same thing, as a TryHackMe user, I go to TryHackMe page, click continue with Google. I'll be redirected to Google login page. I'll provide my Google Gmail account and password. Once I successfully logged in, I'll be asked to grant TryHackMe permission to access my information, and I'll be redirected back to TryHackMe page. In the backend, an authorization code is also sent to TryHackMe server, which will be used by TryHackMe server to exchange for an access token. Once TryHackMe has obtained the access token, it will be using this token to communicate with Google database server where my information is stored. And with this token, TryHackMe can request any information in scope, like my first name, last name, email address, phone number, etc. Okay, so you can start the virtual machine by clicking this. Okay, this is starting the virtual machine. We'll use a customized version of the Django OAuth toolkit for the OAuth provider. It's very important to understand that when the term OAuth provider is used with the upcoming task, it means that the third-party OAuth provider which we want to integrate or authenticate. For example, in the case of login with Factbook, the Factbook is the OAuth provider. Moreover, in this task, the OAuth provider, the coffee shop app, would remain the same. However, the clients, the app we want to integrate, will change in each task. Okay. You can visit this page to see the login panel for the OAuth provider, which would remain the same through the rooms. Okay. We have two sets of the credentials. Right down, right here. So at this stage, we're not required to log in, so we should be good. Let's continue reading. Once you log in the OAuth provider, you can log in any other website just like you perform sign up in Google. Now, visit the URL bistro TryHackMe, which we use to understand the OAuth workflow. We'll understand the workflow by considering a person named Tom. You can use any of the above credentials for him who would like to log in a different website app using the coffee shop app account. Authorization request. Tom first visit the website right here. Okay. OAuth demo. When he clicks on the login with OAuth, coffee shop app must first obtain his permission, so the application redirects Tom's browser to the authorization server with an authorization request. Okay, we'll click this one, click on the button, and you'll be redirected to the authorization server with the URL. I'm going to use CyberChef to decode the URL. Oh, this one's not. Okay, it's going to be easier to understand. So this is going to be the URL right here, and it's important to understand the components of this URL because it will show us if the OAuth service is actually vulnerable to certain kinds of attacks. Response type equal quotes. This right here. This indicates that the coffee shop app is expecting an authorization code in return. State a CSRF token to ensure that the request and response are part of the accept application. Do we have state right here? No, we don't have state right here. So this is vulnerable because a state parameter, even though it's optional, but it always recommended to prevent the CSRF attacks. Client ID is a public identifier for the client application, uniquely identify the coffee shop app. Okay, redirect URI. The URL the authorization server will send Tom after he grants permission. This must match the pre-registered redirect URIs for the client application. So this is going to be the redirect URI, the bistro. Okay. Scope specifies the level of access requested, such as viewing coffee orders. By including these parameters, the bistro app ensures that the authorization server understands what is requested and when to send the user afterwards. Here's a Python code. Okay. Authentication and authorization. When Tom reaches the authorization server, he is prompted to log in using his credentials. This step ensures that the server can verify his identity. After successfully logging in, the authorization server asks Tom if he agrees to grant the bistro app access to his details. This consent step is crucial as it gives Tom transparency and control over which applications can access his data. The process typically involves user login. Tom enters his username and password on the authorization server, which is this page. Consent prompt. After authentication, the authorization server presents Tom with a consent screen detailing what coffee shop app requests access to. Tom must then decide whether to grant or deny these permissions. So let's try that. We can try victim 123. These are the credentials provided at the beginning of the group right here. I'm going to be using this one. It doesn't really matter. We can use either one. See, we as Tom are asked permission to grant access to the coffee shop app, not the bistro. Once we authorize, we take it back to the bistro page. Authorizations and response. If Tom agrees to grant access, the authorization server generates an authorization code. We'll discuss later. The server then redirects Tom back to the bistro website using the specified redirect URI. Alright, so this is expected. We are going back to the bistro websites. The redirections includes the authorization code and the original state parameter to ensure the integrity of the flow. The authorization server responds with the following code. Coffee shop app will use the authorization code to request access token. State the CSRF token previously sent by the coffee shop app to validate the response. Okay, an example of the authorization response would be this one. Okay, so that's what the actual URL looks like. This step ensures the authorization process is secure and the response is linked to the bistro initial request. The authorization code is temporary token that will be used in the next step to obtain the access token, allowing coffee shop app to access Tom's profile details. Token request. The bistro websites exchange the authorization code for an access token by requesting the authorization server token. Authorization server's token endpoint through a post request with the following parameters. The grant types. Type of the grant being used usually is set as code to specify authorization codes as the grant type. Code. The authorization code received from the authorization server. Redirect URI. This must match the original redirect URI provided in the authorization request, the client ID and the client secret, credentials for authenticating the client application. Using the above parameters, the following code will make a token request to -o-token endpoint. Okay. The Bistro app securely exchanges the authorization code for the access token by sending this request. The authorization server will verify the information provided, ensuring the request is valid and originates from the client requesting authorization code. If everything is correct, the authorization server will respond with the access token, allowing the Bistro website to proceed with accessing Tom's profile details. Token response. The authorization server authenticates the Bistro websites and validates the authorization code. Upon a successful validation, the server responds with an access token and, optionally, a refresh token. The authorization server's response include the following: the access token that will be used to access Tom's detail, token type, typically bearer, expiration, the duration in seconds for which the access token is valid, refresh token, which is optional, a token used to obtain new access tokens without requiring the user to log in again. With the access token, the Bistro website can now authenticate requests to the resource server to access Tom's profile's details. The optional refresh token can be used to request a new access token once the current one expires, providing a seamless user experience by avoiding the need for Tom to log in repeatedly. The Bistro website has completed the OAuth 2.0 authorization workflow with the access token. This token is a credential allowing the app to access protected resources on Tom's behalf. Now, the Bistro website can make authenticated requests to resource server to retrieve Tom's profile. Each request to the resource server includes the access token in the authorization header, ensuring that the server recognizes and permits the access. What is the client ID after initiating the OAuth 2.0 workflow? This one. What parameter name determines the time validity of the token in the token response? Expiration. Moving on. Identifying the OAuth services. Identifying OAuth usage in an application. The first indication that an application uses OAuth is often found in the login process. Look for options allowing users to log in using external services like Google, Facebook, or GitHub. These options typically redirect users to service providers' authorization page, which strongly signals that OAuth is in use. Detecting OAuth implementation. When analyzing the network traffic during the login process, pay attention to the HTTP redirects. OAuth implementations will redirect the browser to an authorization server's URL. This URL often contains specific query parameters such as response type, client ID, redirect URI, scope, and state. These parameters can indicate an OAuth flow in progress. For example, a URL might look like this. Okay, because the screen is cut up, we didn't see the full URL, and this is a full URL. It contains the response type, the client ID, the redirect URI, and the scopes and the state. So now this one has the state. Identifying the OAuth framework. Once you have confirmed that OAuth is being used, the next step is to identify the specific framework or library the application employs. This can provide insights into the potential vulnerabilities and the appropriate security assessments. There are some strategies to identify an OAuth framework. HTTP headers and responses. Inspect HTTP headers and response bodies for unique identifiers or comments referencing specific OAuth libraries or frameworks. Source code analysis. If you can access the application source code, search for specific keywords and important statements that can reveal the framework in use. For instance, libraries like Django OAuth Toolkit, OAuth Lit, Spring Security Auth, or Passport in Node.js each have unique characteristics and naming conventions. authorization and token endpoints. Analyze the endpoints used to obtain authorization codes and access token. Different OAuth implementations might have unique endpoint patterns or structures. For example, the Django OAuth toolkit typically follows the pattern /OAuth/authorize and /OAuth/token, while other frameworks might use different paths. Error messages. Custom error messages and debug output can inadvertently reveal the underlying technology stack. Detailed error messages might include the references to specific OAuth libraries or framework. Answer the questions. What is the name of the toolkit used to implement the OAuth in the URL coffee TryHackMe? So let's take a look. Can we infer right here? Let's see. Okay, it looks like it's using Django. Looking at the path right here, it matches this path right here. So Django OAuth toolkit. No. So I guess that's the naming convention. All right, moving on. Let's get to the exercises. Exploiting OAuth, stealing OAuth token. Tokens play a critical role in the OAuth 2.0 framework, acting as digital keys that grant access to protected resources. These tokens are issued by the authorization server and redirected to the client application based on the redirect URI parameter. This redirection is crucial in the OAuth flow, ensuring that tokens are securely transmitted to the intended recipient. However, if the redirect URI is not well protected, attackers can exploit to hijack tokens. Role of redirect URI. The redirect URI parameter is specified during the OAuth flow to direct where the authorization server should send the token after authorizations. This URI must be in the application settings to prevent open redirect vulnerabilities. During the OAuth process, the server checks that the provided redirect URI matches one of the registered URIs. The vulnerability. An insecure redirect URI can lead to severe security issues. If attackers gain control over a domain or URI listed in the redirect URI, they can manipulate the flow to intercept the token. Here's how it can be exploited. Consider an OAuth application with the following registered redirect URIs. So in this screenshot, we see that we have two redirect URIs. One is the bistro.tryhackme at the port 8000, and the other one is the dev.bistro.tryhackme. So there are two redirect URIs. Attacker strategies. If an attacker gains control over the dev.bistro.tryhackme, they can exploit the OAuth flow by setting the redirect URI to http dev.bistro.tryhackme/callback. The authorization server will send the token to this control domain. The crafted attack. The attacker initiates an OAuth flow to ensure that the redirect URL points to their control domain. After the user authorizes the application, the token is sent to this URL dev.bistro.tryhackme instead of the regular bistro.tryhackme. The attacker now can capture the token and use it to access the protected resources. Preparing the payload. From the attacker perspective, before starting the exercise, we have to make sure to log out everything. All right. So http coffee.tryhackme admin log out. Okay, we logged out. For this exercise, we assume that attacker has compromised the domain dev.bistro.tryhackme at port 8002 and can host any HTML page on the server. Consider Tom, a victim whom we send the link. The attacker can craft a simple HTML page, which is called the redirect URI.html with the following code. Okay, only 4 lines, simple. This form sends hidden redirect URI parameter with a value to the compromised domain dev.bistro.tryhackme with the HTML file malicious redirect and submits a request to the coffee TryHackMe OAuth. The malicious redirect HTML page that intercepts the authorization code from the URL using the following code. So this is a script attacker used to intercept the authorization code. Alright, note, since the attacker has complete control over the subdomain, once he redirects a victim to the attacker control domain, he will save the credentials in a database or a file for later usage. Moreover, the redirection from redirect URI of the original URI would be so quick that the victim would have no idea that his authorization code has been hijacked. The attacker can send Tom this link right here. Let's try that. So I received this link in an email, a phishing email. I click on that without paying attention. The victim unsuspecting of the malicious intent, click on the link, which takes to the URL dev.bistro.tryhackme. Let's inspect the URL right here. Yeah, we use the Shabby Chef. Right, as we can see, redirect URI is going back to dev.bistro.tryhackme at port 8002, which is the domain that attacker has a control of. Now, without any knowledge, I am as a victim, we sign in, victim 123, got a typo right here. Well, from a victim standpoint of view, everything is normal. I logged in as usual, and this is from the attacker's perspective. He was able to get the code, and now because the code was exchanged between the servers, the authorization server and the client servers, we as the user in the front end, we had no idea that this process happens. And we got a code, the authorization code. Alright, in the attached VM, when the victim clicked login, okay, we completed this run. From the attacker perspective, they can utilize the intercepted authorization code to make a call to the callback endpoint and exchange it for a valid access token. In an OAuth flow, as we saw earlier, the callback endpoint is always available, accepting the code parameter and returning an access token. With this token, the attacker gains unauthorized access to the user's protected resources. To get the access token, visit this one. Okay, let me copy this one first. This is going to be the code. And we've got the access token right here. We also got a flag. Okay, so that's how attackers intercept token by taking advantage of the redirect URI parameter. Moving on to the next one, exploiting the CSRF in OAuth. The state parameter, as I've mentioned earlier, is very important, even though it's optional, but it has to be implemented or included in the URL to actually prevent CSRF attack. The state parameter in the OAuth 2.0 framework protects against CSRF attacks, which occur when an attacker tricks a user into executing unwanted actions on the application where they are currently authenticated. In the context of OAuth, CSRF attacks can lead to unauthorized access to sensitive resources by hijacking the OAuth flow. The state parameter helps mitigate this risk by maintaining the integrity of the authorization process. The vulnerability of weak or missing state parameter. The state parameter is an arbitrary string that the client application includes in the authorization request. When the authorization server redirects user back to the client application with the authorization code, it also includes the state parameter. The client application that verifies the state parameter in the response matches the one it initially sent. This validation ensures that the response is not a result of a CSRF attack, but a legitimate continuation of the OAuth flow. For instance, consider an OAuth implementation where the state parameter is either missing or predictable. An attacker can initiate an OAuth flow and provide their malicious redirect URI. After the user authenticates and authorizes the application, the authorization server redirects the authorization codes to the attacker's control URI, as specified in the weak or absence of the state parameter. Practical. Yeah, I know it's a bit confusing, but just bear with us. We're going through the example. In this exercise, we'll explore how the absence of the state parameter in the OAuth authorization process can lead to a CSRF attack. You'll need to use the attack box to understand the attack from both the attacker's and the victim's perspectives. We'll be using mycontacts.tryhackme. Before that, we have to log out everything. Okay, we have to add this one to the host entry. Alright, so we added that. Alright, so on the attack box, we go to this URL with the credentials attacker. Once you log in, you'll see a page that allows you to sync contacts to the coffee shop app. Once the accounts are synced, all the current accounts from the client apps are transferred to the coffee shop app account. Not now, so sync contacts. Oh, we have to put this one too. Not 10. You know what? No. Oh. Okay, looks like it's working. Okay, once we click the sync contact, you will be redirected to an OAuth authorization server with the URL, okay, exactly like this. As a pen tester, you will notice that the authorization URL is missing the state parameter, suggesting we can use the same request for a CSRF attack. Let's try and see. Yep. Now it may be a little bit hard to see, so I'm going to decode the URL and go back. Yeah, the state parameter is missing. Here, you don't need to sync your actual account. Let's exploit this vulnerability to attach the attacker's third-party account to the victim. Alright. Exploiting the vulnerability without the state parameter, the authorization process is vulnerable to CSRF. The attacker can exploit this vulnerability by obtaining the victim's authorization code and sending it to the attacker. The authorization server won't have any way to determine whether the authorization code belongs to the attacker or the victim, or whether the request is coming from the attacker or the victim. Preparing the payload. To prepare the payload, the attacker must get his authorization code. This can be done by intercepting the authorization process using tools like Burp Suite or any other network interception tool. So for the purpose of this demonstration, we are provided with this URL that allows us to get authorization code without completing the whole OAuth flow. Not sure if I need those, but just gonna leave them then. No, not this one. So we visit this one. You will get the following response when you visit the above share link to get the authorization with the credentials attacker Tesla123, attacker Tesla 123. Okay, so we got the code. The above authorization code will be enable anyone to get access token against it. The URL parameter in the response is the actual payload that we need to send to the victim. Copy the payload value, which will be used for launching the attack. So now we have the code, right? The verification, the authorization code from the authorization server, and this is the URL. Launching the attack. Once the attacker has obtained the authorization code, he can prepare the CSRF payload. Suppose the attacker sends an email to the victim with a link bistro, which is this URL right here. After receiving the email, if the victim clicks on the link or executes it in the browsers, where XXX is the attacker's authorization, the attacker's coffee shop app or OAuth account will be linked to the victim's account. This effectively transfers all the contacts from the victim's account to the attackers. So in theory, this URL is supposed to work only for the attacker, but because the application, the OAuth URL is missing the state parameter, this URL can now be used on the victim machines, on any other machine, or it can be used by any other users. Because it doesn't have the state parameter, it does not verify whether this code is coming from the attacker or from the victims or from any other users. There's no way for the server, for the authorization server to verify that. So this is going to be the URL that the victim clicks on. Now we go to this one, 80 CSRF. We log in as a victim right here. For the sake of this exercise, since the authorization code is unique, execute the attacker exploit. So from the victim perspective, we go to this page with the credential victim. We log in. What do we have? Now we sync the contact. And I just let attacker, when the victim clicks sync the contacts, he or she will be redirected to the coffee.tryhackme page to actually authenticate himself or herself against the authorization server. And then after he successfully logged in, he will get an authorization code. But for the sake of this exercise, we are going to explore this one right here. Now, because the victim clicked on this one, this authorization code is going to be used in this endpoint to request the access token. As discussed above, the exact link sent to the victim is the URL parameter received during the preparing the payload process. Once executed, the code will make a call to get the access token and sends contacts or messages to the attacker's account. So click on this one. And you see account synced successfully with attacker account. What is the flag value after attaching the attacker's account to the victim's account? Okay, what parameter name does the client application include in the authorization request to avoid CSRF mistake? Moving on to the next vulnerability, exploiting OAuth implicit grant flow. In the implicit grant flow, tokens are directly returned to the client via the browsers without requiring an intermediary authorization code. This flow is primarily used for single-page applications and is designed for public clients who cannot securely store client secrets. However, this flow has inherent vulnerabilities, weaknesses, exposing access token in URL. The application redirects user to the OAuth authorization endpoint, which returns the access token in the URL fragment. Any script running on the page can easily access this fragment. Inadequate validation of redirect URIs. The OAuth server does not adequately validate the redirect URIs, allowing the potential attackers to manipulate the redirections endpoint. No HTTPS implementation. The application does not enforce HTTPS, which can lead to token interception through man-in-the-middle attacks. Improper handling of access tokens. The application stores the access token insecurely, possibly in local storage or session storage, making it vulnerable to access attack or cross-site scripting. Deprecation of implicit grant flow. Due to this vulnerability, the OAuth 2.0 security best current practice recommends deprecating the implicit grant flow in the favor of the authorization code flow with the proof key for code exchange (PKCE). This updated flow provides enhanced security by mitigating the risk of token exposure and the lack of client authentication. Practical. Before starting the exercise, ensure that you are logged out on the OAuth providers as attacker by visiting this one. Okay. We'll do both. No. Copy. Now we have to add to the host file another entry. Nah. TryHackMe will have factbook.tryhackme will have coffee will have bistro.tryhackme. Let's verify everything. Good. In the attached VM machine, visit Factbook, where you see a page that allows you to sync your statuses from Coffee app. So the attached machine is going to be this one, not the attack box. http factbook.tryhackme ADAD. The authorization process will start once you click the Sync Statuses from the Coffee Shop app. The client application is configured to use the Implicit Grant type, which means that the access token will be directly returned to the client. The authorization URL constructed as follows. It has a client ID, it has a URL, redirect URL, it has authorization URL, and okay, so victim perspective. Once the user authenticates using the OAuth provider credentials, which is victim 123. So let's see this one first. Let's forget everything. We have the token right here, response type, client ID. We have redirect URI with the Factbook and the callback. Okay. Once the user authenticates using the OAuth provider, where he can enter a status. This page includes a form for entering a status, submitting it in the AJAX request. So victim 123. Authorize. Okay. For demonstration purposes, the status input field is vulnerable to XSS. Once you reach the status page, enter status like hello, okay. However, we try script alert 1. Attacker perspective. To prepare for the attack, inside the attack box instance, run a Python HTTP server on this port, and the attacker will share the following payload with the victim, as he will enter status. Okay, let's see what it does. So the JavaScript payload starts by extracting the fragment identifier from the URL, okay, which is a part of the URL followed by the symbol $sign. It removes the leading pound using the substring 1, which is this one right here. This string is then split by the ampersand sign to separate the individual key value pairs. The reduce function processes each of the pairs, splitting them into further by the equal signs to isolate the keys and the values. These key value pairs are stored in the object called the results, which is right here. The whole thing right here. The script extracts the access token value from this object and assign it to the variable access token. Okay, let me extend the machine so nothing is interrupted. Okay, the script extracts the access token value from this object and assigns it to the variable access token. To exfiltrate this access token, the script creates a new image object and sets it to a source attribute to the URL that points to the attacker server, which is this one, 10.10.145.17. When the image is loaded, it triggers a request to the attackers. So we don't need this one on the attacking box. We just need it as a payload on the victim sides. So what's the attack IP address? We have 10.10.145.17 and the port 8081. Cool. So we copy this whole thing and put it into the victim's machines. But before we do that, we have to set up a Python listener on port 8081. Now this listener is listening on port 8081, waiting for any incoming data. Now from the victim perspective, as a pentester or attacker, they stumble across this page. They figure out, well, this page is vulnerable to XSS, so they're going to inject this script right here. This is called store XSS. We submit it. So right now it doesn't show anything. Nothing happens. But once we refresh the page, it will send the data to our attacker listener right here. That's the concept behind this attack. The implicit grant tab is particularly vulnerable to such attack because the access token is exposed in the URL fragment, making it accessible to any script running on the page. This vulnerability is compounded if the application does not enforce HTTPS, leading to potential token interception through man-in-the-middle attacks. What symbol separates the access token from the OAuth 2.0 implicit grant flow? $. Visit this one and validate the access token. What what's the cookie? This one is a cookie. Or access token. Alright, so we got the flag. Never mind. TryHackMe token hacked. Alright, all the vulnerabilities and evolutions of OAuth 2.1. Apart from the vulnerabilities discussed earlier, attackers can exploit several other critical weaknesses in OAuth 2.0 implementations. The following are some additional vulnerabilities that pentesters should be aware of while pentesting an application. Insufficient token expiry. Access token with long or infinite lifetime poses significant security risk. If an attacker obtains a shutter token, they can access protected resources indefinitely. Implementing short-lived access token and refresh tokens help mitigate this risk by limiting the window of opportunity for attackers. Replay attacks. Replay attacks involve capturing valid tokens and reusing them to gain unauthorized access. Attackers can exploit tokens multiple times without mechanism to detect and prevent token reuse. Implementing nonce values and timestamp checks can help mitigate replay attack by ensuring a token is used only once. Insecure storage of tokens. Storing access tokens and refresh token insecurely can lead to token theft and unauthorized access. Using secure storage mechanisms such as secure cookies or encrypted databases can protect tokens from being accessed by malicious actors. The evolutions of OAuth 2.1. OAuth 2.1 represents the latest iterations of the evolutions in the OAuth standard, building the foundations of OAuth 2.0 to address its shortcomings and enhance security. The journey from OAuth 2.0 to OAuth 2.1 has been driven by the need to mitigate known vulnerabilities and incorporate best practices that have emerged since the original specification was published. OAuth 2.0, while widely adopted, has several areas that require improvement, particularly in terms of security and interoperability. Major changes. OAuth 2.1 introduces several key changes aimed at strengthening the protocol. One of the most significant updates is the deprecation of the implicit grant type, which was identified as a major security risk due to token exposure in URL fragments. Instead, OAuth 2.1 recommends the authorization code flow with a PKCE for public guides. Additionally, OAuth 2.1 mandates using the state parameter to protect against the CSRF attacks. OAuth 2.1 also emphasizes the importance of secure handling and storage of tokens. It advises against storing tokens in browser's local storage due to the risk of XSS attacks and recommends using secure cookies instead. Moreover, OAuth 2.1 enhances interoperability by providing clearer guidance on the redirect URI validation, client authentication, and scope validation. In summary, OAuth 2.1 builds on OAuth 2.0 by addressing its security gaps and incorporating best practices to offer more secure and protected authorization framework. For more details and information on OAuth 2.1, you can refer to the official specification, which can be found here. Answer the question, which of the following has been omitted from OAuth 2.0? That's going to be implicit grant. Alright, conclusion. In conclusion, this room on OAuth has provided a detailed understanding of the OAuth 2.0 and its significance in modern web applications. We discussed the fundamental concepts necessary to understand OAuth, including various grant types and OAuth flow. We then explore how to identify OAuth services within an application. Throughout practical exercises, we exploited various vulnerabilities associated with OAuth 2.0, including weak implementations of the implicit grant float, the effects of unmanaged redirect URI, and the non-availability of scope parameter. These exercises highlighted the critical nature of securing OAuth implementations and the potential risk of common misconfigurations. Finally, we examined all the vulnerabilities and discussed the evolutions of OAuth 2.1, emphasizing its improvements and how it addresses the shortcomings of OAuth 2.0. This room has equipped you with the knowledge to identify and mitigate risks associated with OAuth from the lens of the pen tester and secure coder. In my opinion, it's a little bit technical for a lot of people. I mean, even for me, it took me several attempts to actually go through the room and understand the concept. So if you have any question, feel free to reach out to me. I'll be happy to help. Alright, next time then, bye.